Hello everyone. I'm Gitanjali Jaina. I made a PMR FTA for this course, which is Physics of Linear and Nonlinear Optical Waveguide. As I said before, in each live session, we'll discuss few problems that is related to the concept that has been taught in this week, as well as I will also try to clarify the doubts that you must be having about the assignment or any concept or whatever you want to ask related to the concept that is related to this field. So, let me get started. So, before starting the today's tutorial, so you must be knowing the solution of assignment one and assignment two. Both are released in the NPTEL website. So let me ask whether you have any doubt in the solution, or if you have any doubt, then I will try to clarify now. I will try to go through the doubts that you have for the assignment. Otherwise, I will start directly from the questions. Okay. So, Niranjan, let me know whether you have doubt in the assignment one and two. Okay. So, then I will start directly. So, let us see what we have in question one. Question one, it's about a parabolic index fiber, which is refractive index N1, 1.5, delta 0.01, and the core radius, it is 50 micrometer. Assuming that the ray is launched as shown in the following figure, calculate the amplitude and the period of the ray paths for theta 0 is 1, 4, and 8.13 degree. Okay, so this is the expression for parabolic index medium, it's already given. Uh, this you have to remember. So n square x, it's the variation is inside the core is like this, and in the cladding, it's a constant. It is equal to n2 square. So let us start. So if you recall, we have the ray path equation, which is d square x by dz square. So it's always a good practice to start from the ray equation because you don't know what is the profile of the refractive index that is given in the exam. So always start with the ray equation. Then you can incorporate the refractive index profile to find out what is the solution for the ray equation. So n square x, it's already given inside the core. It is n1 square, 1 minus 2 delta x by a square. So that means we can get the first derivative as minus 2 delta n1 square 2x by a square. So that means this is minus 4 delta n1 square a square x. So we got what is there in the right hand side. So I'm writing this equation just to recall you what has been taught in the course. Okay. So now the ray equation, it's d square x by dz square. It is minus 2 delta n1 square by a square beta tilde square x. And this, the solution fits, let's say it is some constant gamma minus gamma square x. So solution for this equation, it's already known. It's a sinusoidal function So x of z, you can write it as a sine gamma z plus b cos gamma z. And the value for a and b, if you recall, we can find out using the boundary conditions. So what are the boundary conditions that is given? So it is given, assuming that the ray, it is launched as shown in the following figure. So if you see, the ray is launched at the origin, that is x equal to 0. When x equal to 0, z is also 0. So that means we can put x 0, it is 0. This is the boundary condition 1. So if you put x equal to z equal to 0 in this equation, then the a part, it is always, it is 0. And the second part, it is b. So that means the constant b is 0 for this case. So what we have now is xz is a sine gamma z. So the second boundary condition that we have is the slope of the array that it makes during the when it is initially incident on the core. So it is given. So if you see, it is theta 0. So that means tan theta 0 is dx by dz at z equal to 0. So dx by dz, it is nothing but minus a gamma cos gamma z plus b gamma. So it is not minus, it is plus gamma a gamma cos gamma z, and this is minus b gamma sine gamma z. So if you put z equal to 0, this part is already 0. What we have is a gamma. So here we can find out what is the amplitude of the propagating ray path, which is tan theta 0 divided by gamma. So here you can see how the launching angle, it is related to the amplitude. So it's better to remember this relation so that you can compare the ray path and their amplitude. So the final form that we have now, it is a x z. The ray path, it is a sine gamma z, and it is tan theta 0 by gamma sine gamma z. This is the ray path. Now the question is asking about what is the amplitude of the wave when of the ray when theta 0 is 1 degree, 4 degree, and 8.13 degree. Okay. So before calculating the amplitude as well as the periodic length, that is LP. So amplitude, it is given tan theta 0 by gamma, and gamma, it's from the equation, it's gamma is n1 a beta tilde root over of 2 delta. So it is root over of 2 delta n1 beta a by a beta tilde. Okay, so now here if you want to express a in terms of the launching angle only, so if you see here gamma, you can write beta tilde as initial condition is n1 cos theta 0. So that means if you put n1 cos theta 0 here, so you have root over of 2 delta by a cos theta 0. So it is completely in terms of the launching angle. So that means gamma, we have root over of 2 delta a cos theta 0 And A now it is tan theta 0 over gamma, which is root over of 2 delta A cos theta 0. So cos will cancel. We have A sine theta 0 by root over of 2 delta for the amplitude. And for the periodic length, if you recall, it is LP equal to 2 pi over gamma. So it is 2 pi A cos theta 0 over root over of 2 delta. So here all the factors we have known, theta 0 we know and delta is already given. Uh, so we can easily calculate it. But before doing the calculation, it's a you you have to check whether the angle, whether the incident angle, it is satisfied in the condition for ray guidance. So for a graded index fiber, the condition for ray guidance, it is beta tilde, the ray constant. It should lie between the highest refractive index n1 and the lowest refractive index, which is n2. So beta tilde should lie between n1 and n2. Okay. So that means n2, it is beta tilde is n1 cos theta 0. So that means if you divide it by n1, so it is cos theta 0 and 1. So that means when we take a cos inverse, so this sign will change, right? So this means cos inverse n2 by n1 should be greater than theta 0, should be greater than cos inverse 1 is 0 degree. So this is the condition for the ray guidance. So let us see what is the n1 and n2. So n1 it is already given. Let me see. N1 is 1.5. It is given in the question. And N2 it is not given, but you can calculate it from the relation. N2 is N1 1 minus 2 delta, right? 2 delta half. So N1 is given, it is 1.5 and delta I think it is 0.01. Yes, it is 0.01 it is given. So is 1 minus 0.02 per half. And if you calculate it, it will come around approximately 1.484924. So that means if you now calculate the range of theta, so this will be cos inverse n2 by n1, which it is 1.484924, 1.5 theta 0 is this is 0. And the value for this relation is 8.1301 degree. So this is the final form. What is the range of theta for the ray guidance? So if you see now, we have theta 1 is 1 degree, 4 degree and 8.13 degree, which satisfy this relation. So that means all the rays will be guided inside the fiber. Now we can proceed to calculate what is the amplitude and what is the periodic length. So for A, which is theta 0 is 1 degree. So we have seen A is amplitude is A sine theta 0 root over of 2 delta. So A is given 50 micrometer sine 1 degree over 0.02 and this will come around 6.17 micrometer. And similarly, we can find LP. which is 2 pi a cos theta 0 over root 2 delta. So this is 2, 3.14, 50 cos 1 root over of 0.02. So this is 2.219 millimeter. Okay. So now let us see what is the values for 4 degree. So theta 0 is 4 degree now. So that means A will be A sine theta 0 over root over of 2 delta, which is A sine. So let me put it is 50 micrometer sine 4 degree over root over of 0.02, and this will come around 24.66 micrometer. And LP, it will be 2 pi A is 50 cos 4 degree over root over of 0.02. So this will be around 2.214 millimeter. So here you can see the angles are small. So when angles are small, you can see the periodic length. There is a little difference between the periodic length. Although the amplitude is high, but the periodic length, it is almost, they are close to each other. So if you plot a graph for a path, it will be like for theta 1, and this will have, sorry. So let us say this is for 1 degree, and for 4 degree, this will have the LP, it is almost same, but amplitude is high. Okay. If the question asks about the ray diagram, then you can easily identify. So let us see what we have for theta 0 is 8.13 degree. So A is A sine theta 0 over root over of 2 delta. A is 50 micrometers sine 8.13 over root over of 0.02, and this will come around 50 micrometer. 50 micrometer, almost it is 50 micrometer, and B LP is 2 pi A cos 8.13 degree 0.02, and this will come around 2.198 millimeter. Okay. So here one thing that you can notice is amplitude here for this ray is 50 micrometer. And 50 micrometer, it is already given, it is the value for the core radius. So that means at this angle, it is already touching the core cladding interface. So that means any angle, that is if you incident one ray that a value theta greater than theta 0, so it will be refracted to the cladding interface. So this is theta 0, it is already 50 micrometer. Now if you incident a light greater than theta 0, it will be refracted to the cladding interface. Okay, it will not be guided inside the fiber. So this is what question second says. So questions, the second question is about in the above question, so that for theta 0 greater than 8.13 degree, the ray will be refracted away. So one thing that we have seen before is its amplitude is already 50 micrometer. That is why it will be refracted away. And other condition for the refraction is the beta tilde. It should be greater than, it should be less than N2. When the beta tilde is less than N2, then that ray will not be guided. It will be refracted into the cladding interface. So beta tilde, we know it is N1 cos theta 0. This is N2. So that means cos theta 0, it should be N2 by N1. So theta 0, it should be greater than cos inverse N2 by N1. And N2, N1 we have already calculated it. It is cos inverse 1.484924, and this is 1.5, and if you calculate it, it will come around 8.13 degree. So that means when theta 0, it is greater than 8.13 degree, then that ray will be refracted into the cladding interface. Okay. And this is the condition for the refraction. We have condition for guidance, which is it should lie between N1 to N2. And when the beta tilde becomes less than N2, then that ray will be refracted. Even if I don't have TIR, shouldn't there be a partial action for this case, for this refraction? So what I mean, are you talking about when theta 0 is 8.13 degree, then there will be partial reflection into the, okay. So one thing that you have to remember is that the TIR, sorry, the reflection only occurs whenever the critical condition is satisfied. That is phi is greater than equal to phi c. Only when this will be reflected back to the core medium. Other than that, it will be refracted away. And at this, I think in this refraction condition, it will be any possibility of reflection in this case. So only if you, I don't think there will be reflection in this case, but only if you consider the TIR, when TIR occurs, it says that complete reflection of energy back to the core medium. But in TIR case, we have seen there is a refracted wave into the cladding interface, which is exponentially decaying. It's a evanescent wave, but it's not the other way around. Like if it's not satisfying TIR, then there will be always there will be refraction, not reflection. But in case of TIR, there will be refraction as well as reflection. Okay, so I hope it's clear. Otherwise, let me confirm this situation in the next tutorial. So I think there won't be any reflection, but let me confirm you in the next tutorial. Okay. So, okay, then let us move to our next question. Please go through the question once. This is also based on a parabolic index medium. So today we will mostly deal with parabolic index medium. There are different type of wave propagation in a parabolic index medium. Because in step index you already know it's a straight line, but in parabolic it is sinusoidal. So it is given, this is the usual expression for the parabolic index medium, which is refractive index. The maximum it is N1 is 1.47. It's also known as axial refractive index. That is around the axis of the fiber, it is N1. And delta it is given 0.01 and A is 40 micrometer. The first part is calculate the range of theta values for the guided rays. If the rays are incident from a point x equal to 20. So let us say this is the point here. This is x equal to 20. So rays are incident from here, this point, instead of the axial position. Um, Rays are incident from x equal to 20 micrometer in the x-straight plane. Assume theta 0 is the angle which is made by the tangent to the ray with z-axis. That means this is theta 0, not theta 0, theta. So the question is asking, when you launch a light at this position, other than the axial point, then what is the condition for ray guidance? So condition for ray guidance, it is nothing but beta tilde. It should lie between N1 to N2. Okay. Now the N1 here, it is not the axial refractive index because beta tilde it is given by Nx cos theta x, right? It is the ray path constant. So beta tilde it is given by this. Now uh, at x equal to 20, what is the maximum refractive index that the beta tilde, what is the maximum value beta tilde can have? So beta tilde can have nx when x equal to 20. Okay. So that means the n1 here is nx at x equal to 20. Not n1. So that means now we have, so let us see, this is nx x equal to 20. Beta tilde, you can write it as nx x equal to 20 cos theta that we want to find out. And this is n2. So just divide it by nx at x equal to 20. It will get 1. And this is cos theta. And this is n2 nx at x equal to 20. So that means now the theta value will lie between cos inverse 1 less than theta less than cos inverse n2 nx at x equal to 20. So cos inverse 1 is 0, theta, and this is cos inverse n2. So we need to find out what is n2 and nx at x equal to 20. So n1 at x equal to 20, you just need to put the formula. It is n1 1 minus 2 delta x by a. X is 20, A is 40 square. How? So N1 it is given, I think it is 1.5, no, 1.47. So it is 1.47, 1 minus 0.02 over 4. Up. And this will come around 1.466320. So this is the value for N1 at x equal to 20, and N2, this is the usual expression N1 1 minus 2 delta half. N1 it is 1.47 and it is 0.02 power half, and this will come around 1.455225. Okay, so now the cos inverse N2 it is 1.44455225, and this is 1.466320, and this will come around 7.05 degree. Okay, so if you put here, that means theta should lie between 0 to 7.05 degree. Okay, so I think this part is clear to you. We'll move to the next part. So this the question says, what would be the angle theta at x equal to 20 for rays corresponding to the mode with effective index beta by k0 is 1.46. So which mode at x equal to 20 will correspond to this mode in effective index? So the beta tilde, that is we call it as a ray constant, it is also known as the mode index. Okay. So beta tilde is given 1.46. And if you recall, beta tilde, it can be written as nx cos theta x, which remains constant during the wave propagation. It is 1.46. So nx, so this is at x equal to 20. So that means cos theta x would be 1.46 over nx at x equal to 20. This we have already calculated. It will come around 1.46320. So this is 1.46 over 1.4632. So that means theta x would be cos inverse 1.46, and this will come around 5.32 degree. So when you incident the ray at this angle, the beta tilde for this array, which we call also effective index, it is 1.46. Okay, let us move to our next part. So the question says, assuming rays are incident at an angle theta from the z-axis at x equal to 0 at the input end of the waveguide, that is at z equal to 0, calculate the period zp for the ray path for theta equal to 1, 4 and 8.131 degree. So now the rays, if you recall in the first question we have solved what is the general solution for the ray path in a parabolic index medium, which is x z is a sine gamma z plus b cos gamma z. And when rays are incident from x equal to 0 and z equal to 0, it is x0 sine gamma z. And the periodic length zp, it is 2 pi over gamma, and we have seen this is 2 pi a cos theta over root over of 2 delta. And as I said before, we need to calculate what is the uh, condition for the guidance. So before calculating the ZP and the amplitude, it's a good practice to first find out what is the range of beta. Okay. Or you can other thing that you can do is what is the at which angle the ray will get refracted. So the for refraction to the cladding, we have beta tilde less than n2. This we have. So that means at nx cos theta x at x equal to 0 is less than n2. So nx at x equal to 0, it is n1, and this is cos theta. Let's say it is theta 1 less than n2. So that means cos theta 1, it is less than n2 by n1. And n2, it is n1, 1 minus 2 delta to our half, right? And this is n1. So this will cancel. No need to find out what is n2 here. So what we have now, so cos theta 1, it is less than 1 minus 2 delta to power half. Delta is already given. So that means theta 1 must be greater than cos inverse 1 minus 2 delta is, so what is delta in the question? It is 0.01. So that means is 0.02 power half. And if you calculate it, it will come around 8.13 degree. Okay. So that means when theta, it is greater than 8.13 degree, it will be refracted to the cladding interface. So we have angle 1 degree, 4 degree, and 8.131 degree. So here you can see this theta value, it is greater than 8.13 degree. So that means there will be no guidance for this ray. So we don't need to calculate the ZP here because here no guidance of ray. So that means we just need to find out what is the ZP for theta 1 equal to 1 degree. Here you can see how uh, tricky the question may be. It's like it may ask about a angle where the ray is getting refracted. Now you just use the formula to find out what is the ZP, and it will be a wrong answer. So for 1 degree we have 2, 3.14, and A it is given 40 micrometer cos 1 degree over root over of 0.02. And this will come around 1776 micrometer. And for theta 2, you can easily calculate because it is getting guided. So we can use the formula ZP equal to 2 pi A cos 4 over root over of 2 delta So just put the values of A and delta. This is 40 cos 4 0.02, and this will come around 72 micrometer. Okay. So I hope this problem is also clear to you. Okay. So we'll move to the next question. So we'll see in this tutorial, we'll see different situation where the ray path equation is different, where the numerical aperture of the fiber of the parabolic index fiber is also different. So depending on the point where you incident the light, the numerical aperture for the ray guidance will be different. So we'll see in details in this tutorial. So this question says a ray is launched parallel to the z-axis at x equal to x0. What is the ray path equation for the ray propagating inside the parabolic index fiber? So that means it's a guided ray. So let us see what we have here. And it is incident at x equal to x0. So if you recall, we have n square x and 1 square, 1 minus 2 delta x by a square. So dn square by dx is minus 4 delta and 1 square s square x. So we have the ray equation. Ray path equation is 1 minus 2 delta 2 beta delta square dn square by dx. So this, after putting this, you can write it as a minus gamma square x. So the general equation we always get is a sine gamma z plus b cos gamma z. This is the general form. Now let us see what is the initial condition. It is given the ray is incident at x equal to x0 at z equal to 0. This is the first boundary condition. So if you put this boundary condition here, so that means x0, it is x0, right? So x0 will be a sine 0 plus b cos 0 equal to x0. So that means this is 0 and this will give b equal to x0. So we have the ray path equation now is xz is a sine gamma z plus x0 cos gamma z. Now what is the second ray path equation? So it is about the slope of the ray. So tan theta 0 at x equal to x0, it is dx over dz at z equal to 0. So dx by dz will be a gamma cos gamma z plus x0. So this will be minus gamma sine gamma z at z equal to 0. So this will be 0. Only this part will give a gamma. So that means we got the amplitude as, for this case also we got amplitude 10 tan 0 over gamma. But if you see the question, it is given array is launched parallel to the z-axis at x equal to x0. So that means the theta 0, it is 0 because it is parallel. So this will give tan 0 over gamma, which is 0. So the A part of the amplitude is 0 now. So that means the ray path equation for this case, it is x0 cos gamma z. Okay. So in a fiber, when you incident a light at the axial point, the ray path equation is like A sine gamma z. But when you incident the light, so it must be parallel also. When you incident a parallel light at non-axial point, then the ray equation is x0 or some constant cos gamma z. So this is the answer for this question. And this ray path will also help you to find out what is the period, what is the amplitude, and what is the time period of the ray path. Okay. We'll see one question where this ray path is useful. So let us move to our next problem. So the question says, in a parabolic index medium with a refractive index n1, it is 1.5, delta it is 0.01, A it is 50 micrometer. Array is launched parallel to the z-axis at x equal to 15 micrometer. So this situation is similar to the previous one, third question. So what we have now is, let us draw the schematic. This is Nx and this is N2. And array is incident at x equal to 15 micrometer. And sorry, it is launched parallel to the x-axis, not at an angle. So, and the question asks, what is the angle that the ray would make with the z-axis at x equal to 7.5 micrometer, and find out the period of the ray path and draw the ray path. So if you recall, it is the beta tilde. Theta 0, it is given 0 degree, right? So that means beta tilde will now become nx cos theta x at x equal to 15 micrometer. This is 1. So beta tilde would be nx at x equal to 15 micrometer. Now we already know this beta tilde. So whenever the ray propagates inside the parabolic index medium, this beta tilde, it remains constant. Only the refractive index and the angle theta, they vary such that the product of this refractive index and the cos theta, it makes the beta tilde constant. So that means at x equal to 7.5 micrometer, where we want to find out the angle. So here also the beta tilde will be equal to nx at x equal to 15, right? So this must be equal to nx at x equal to 7.5 micrometer, and there is a angle cos theta x at x equal to 7.5 micrometer. And it is asking about what is the angle. So we just need to find out what is the refractive index at this 15 micrometer and 7.5 micrometer. So cos theta x is equal to 7.5. It would be now nx x equal to 15 over nx at x equal to 7.5. And nx at x equal to 15, you can write it as n1, 1 minus 2 delta x1 by a square up over n2. Sorry, this is n1 only. N1, 1 minus 2 delta x2 by a square half. X1 I have taken, it is 15 micrometer, and x2 is 7.5 micrometer. So n1 will cancel. So what we have now, it is 1 minus 2 delta 15 by 50 square half, and this is 1 minus 2 delta 7.5 15 square. So just calculate it. Delta, it is already given in the question. It is 0.01. So that means if you put 0.01 here, 0.01 here, you will find this ratio. It is approximately 0.9991 over 0.9998. So this is cos theta. It's equal to 7.5. Now to find theta, just take the cos inverse. So cos inverse of 0.9991 over 0.9998. So this will come around 2.14 degree. So because in this question it's already given, it is a guided ray. So that means this angle will be guided inside the fiber. So let us see what is the period for this case now. So finding the period of the ray. So period will be remain same because it depends on ZP is 2 pi over gamma. Okay. And if you recall, is 2 pi a beta tilde 2 over of 2 delta over L1. And if you put the values, it is 2 into 3.14. A is 50 micrometer, and beta tilde, it is nx, which is 0.9991, is 0.02 over 1.5. And this will come around 29.58 micrometer. Okay. And the third is about the ray path. What will be the ray path here? So if we recall the general solution, we have it is A sine gamma z plus B cos gamma z. But when you incident a light, in the third question we have seen, when you incident light parallel to this non-axial point, then only this part will define the ray path. And we have seen this is x0 cos gamma z, right? So it behaves like a cosine function. So that means the ray path will be it is 15 micrometers. So this will be like this. And LP here is the distance between this peak value. LP or Z peak, I think. And this is 15. And the core radius is 50 micrometer. Okay. I think this problem is also clear. We'll move to the next part then. So the question is asking about what is the numerical aperture of this parabolic index fiber when you launch the light at the axial point or when you launch the light at the non-axial point. So the question is consider a parabolic index waveguide with the refractive index N1 and 2 and A is given. Calculate the numerical aperture at the axis and at a point 20 micrometer from the axis. So let us see. So we have n square x. This is n1 square. Please recall this, remember this formula. X by a square mod x less than a. And it is n2 square when mod x greater than n. And if you recall, numerical aperture is nothing but the what is the maximum sine angle that is that will be guided inside the fiber. So this is defined the sine I max. So if you recall, for guided rays, we need beta tilde should be greater than n2, right? So it's the general is like it should be lie between n1 to n2. So let us see the second part, beta tilde greater than n2. So that means this is nx cos theta x should be greater than n2. So the first question is the ray is incident at the axis of the fiber. So what is the refractive index there? At the axis of the fiber, we have nx equal to n1, right? At the axis, nx is equal to n1. So that means this equation becomes n1 cos theta 1 should be greater than n2. So cos theta 1 is greater than n2 over n1. Now You just need to change this equation such that you can use the Snell's law and find out what is the maximum of sine angle. So cos theta, you can express it as 1 minus sine square theta 1 should be greater than n2 over n1. So this is, if you rearrange it, it is sine square theta 1, it's less than 1 minus n2 square and n1 square. So that means n1 square sine square theta 1, it is less than n1 square minus n2 square. And this here you can use the Snell's law. It is na square sine square I1 less than n1 square minus n2 square. So that means we have sine square I1 is n1 square minus n2 square over na. So if you find out what is the I max will be, so let us see what is I1 now. I1, it should be less than sine inverse square root n1 square minus n2 square over na. So this is the I max value, which is, so the question was asking about numerical aperture. So that means na, it is sine of I max, which is nothing but square root n1 square minus n2 square. So at the axial point, it is similar to what we have in the step index fiber. So this is n1 square minus n2 square. N1 square is 1.75 square and n2 it is given 1.677 square. So this will come around 0.5. So let us see what we have in the second part. So second part, the ray is incident at a point, at an non-axial point x equal to 20 micrometer from the axis. So that means when you incident the light at this at that point, the beta tilde at that point should be greater than n2. Now the beta tilde, you can write it as nx cos theta x at x equal to 20 should be greater than n2. So now we have cos theta x should be greater than n2 over nx. So just substitute cos theta as sine square 1 minus sine square theta x. So it is n2 over nx. So that means this will give 1 minus sine square theta x. So sine square theta, it will be less than n square x minus n2 square over n square x. So n square x, I can keep it here. So this you can use the Snell's law. So Na, it is already 1. If nothing is given, so I'll take it as a 1. So it will be sine square Ix should be less than n square x minus n2 square. So sine Ix, it would be square root n square x minus n2 square. So here you can see at non-axial point. So at non-axial point, let us say point here, the numerical aperture depends on the refractive. So N1 is gets substituted by Nx. Okay. So instead of N1, we have Nx here. So Na is now sine of I max. It is n square x at x equal to 20 minus n2 square. So just find out what is the value of nx at x equal to 20. Then n2 is already given. It is 1.677, and n1 n square x you can find out using n1 square. 1 minus 2 delta x by a. X is 20 and a is given 25. And n1 it is given 1.75. So just put it, you will get n1 square is, I think it will come around, let me see, 2.9024. So delta was not given in the question, but you can calculate it delta because n1 and n2 is already given. So delta you can calculate is n1 square minus n2 square over 2n1 square. So that means you need to find 2 delta. It will be n1 square minus n2 square over n1 square. So n1, n2 we already know. So if you calculate it, it will come around 0.081688. After putting delta, we will get n1 square is 2.9024. So that means we have numerical aperture. It is 2.9024 square minus n2 1.677. So this will come around 0.3. So you can see at the non-axial point it is 0.3, but at the axial point we have it is 0.5. So it is vary from point to point in the parabolic index medium. I think this problem is clear to you. We will please go through question 6 once. The question is also based on the same parabolic index medium. So it is N1 1.5, delta 0.01, and A is 50 micrometer. So assuming at x equal to 0, it is 0, plot the ray paths for x z equal to big. When beta delta is 1.5, 1.49, 1.4849 and 1.47. What will be the ray path for this ray constant? So as I said before, It's always a good practice to start with the general ray equation, that is x z is a sine gamma z plus b cos gamma z. So now you can see the ray is incident at the axial point. That is at x equal to 0, it is 0. So that means the exit now it will be a sine gamma z. There won't be any cos part. Okay. And before drawing the ray parts, let us see what is the allowed values of beta tilde for a guided ray. So beta tilde, it is nx cos theta x. And for guided ray, we have beta tilde. It should be greater than n2, or and it's in the between n1 and n2. So that means we need to, n1 is already given, we need to find out what is n2 now. So n1 is given, it is 1.5, n2, this is n1, 1 minus 2 delta up. So it is 1.5, 1 minus 0.02 power half. And if you calculate it, it will come around 1.484924. So that means for guided ray, we have beta tilde, we should beta tilde should lie between 1.4 to 1.484924. Now let us see what is the beta tilde given here. So one is 1.5, 1.49, 1.4849 and 1.47. So beta tilde is 1.5, 1.49. So if you see the ray guidance, these values, it lies in the guided ray equation. No, this one doesn't lie. Only these two lies in the guided ray wave equation. These two doesn't lie in the condition for ray guidance. So that means these two will be refracted to the cladding, to the cladding. Yes, 1.5 it will be guided, because if you recall 1.5 it corresponds to the point where the launching angle is 0. So this is axial ray. This will be guided. This is not a axial ray, but this is a guided ray. So now, depending on this, just plot the graph. So we have, let us say, this one. So this is nx, this is n2. So the first part 1.5, it's a axial ray, so that means this will go like this. So it is maximum value of beta tilde. So beta tilde is 1.5. And for the second ray, we have theta beta tilde 1.49. So that means this will be like this. It's a sinusoidal. So this one is for beta tilde 1.49. And other rays like for 1.49 and 1.47, this will be refracted to the cladding. Okay. So always calculate the range of beta tilde, then only you should proceed to calculate what is the amplitude, how the wave propagate, and what is the time period, as well as what is the periodic length. So let us move to our next problem then. So next problem is about intermodal dispersion. So it's a step index fiber, which is refractive index N1 is 1.5, and it is given N1 minus N2 over N2. It is 0.01. Find the intermodal dispersion between two guided rays after traversing a distance L equal to 1 kilometer. So there is a figure also given. It is given the two guided rays are like this. One is incident at an angle I1. This is I1. And other ray, it is incident at angle I2. I2. So the question is asking about what is the intermodal dispersion between these rays. It's- N2 is not given, but you can calculate it. So let us see what we have. So here, if you put this is N1 minus N2 minus 1, it is 0.01. So that means N1 is 1.5, N2 it is 1.01. So here N2 that we got is 1.5 over 1.01. So this will be approximately 1.485148. So now to find out the intermodal dispersion, you need to find out what is the time taken by this rays to travel the distance 1 kilometer inside the fiber. So you can't use the final formula that we have has been derived in the class. So it was derived by considering the minimum time that the ray can take and the maximum angle that the ray can take. So here it is different. So you need to find out what is the time for individual wave. Then you just take the subtraction between this time to find out the intermodal dispersion. Okay, so what we have, if you recall, so when we have a ray like this, and this is incident angle phi, this is also phi, A, B prime, B, C. So to travel from A to C, the distance covered is AB plus BC. So that means the time taken by the ray to go from A to C, it is AB plus BC over velocity, right? And it's a step index fiber. That means you can write it as a C by N1. So time T, it is given by AB plus BC N by C. And in this figure, so we have to express AB and BC in terms of the length of the fiber. So we have to relate AB plus BC to AC. And if you see this diagram, AB prime B, you can write AB as AB prime by sine phi and BC as B prime C by sine phi. So that means we have N by C of AB prime plus B prime C sine phi. And AB prime plus B prime C, it is nothing but AC, the part of the fiber length. So N AC by C sine phi. So to travel from A to C, it takes time NAC by C sine phi. That means to travel L distance of the fiber, what will be the time? It is NL. This is N1, right? Co-refractive index. So N1L C sine phi. So this will be the time, total time taken by the ray to transverse L length of the fiber. And it is already given, L is 1 kilometer. So everything, now we know everything. N1 is given, L is given, C, we know it is 3 into 10 to the power 8 meter per second. And I think we just need to find out what is sine phi. So in the problem, it is also given, I forgot to write I1, it is 7.06 and I2, it is 11.3. So using I1, I2, we can find out what is phi 1, phi 2. So, so that means, so to calculate phi, I1, it is given 7.06 degree. So if you use Ness law, sine I1 is N1, sine theta 1. So that means theta 1 is sine inverse. Sine I1, it is 7.06 over N1, it is given 1.5. And this will come around 4.7066. So that means phi 1 in a step index fiber, if you recall, it's a the path is a straight line. So that means you can write phi 1 is 90 minus phi theta 1. So phi 1, it will come around 85.2933. This is phi 1. So that means now the time t1, it is n1 L by C sin phi, n1 L by C sin phi 1. So it is 1.5, 1 kilometer. C is 3 into 10 to the power 5 kilometer per second, and this is sine 85.29. And if you calculate it, it will come around 5.02 microsecond. This is for the first ray. Now for the second ray, we have I2 as 11.3. So that means we can calculate theta 2 as sine inverse sine I2, which is 11.3 over N1, which is 1.5. And if you calculate it, it will come around 7.506048. So now phi 2 will be 90 minus theta 2, right? So this will come around 82.493956 degree. So now we have everything. So T2 we can calculate. It is N1L C sin phi 2. So it is 1.5, 1 kilometer, and C is 3 into 10 to the power 5 sin 82.493956. And this will give a value 5.04 microsecond. So earlier we have 5.02 microsecond. Now it is 5.04 microsecond. So that means delta T, because of the different time, it is approximately 0.02 microsecond. And in terms of nanosecond, you can see this is 20 nanosecond. So that means the ray uh, 2, uh, it will reach the endpoint after 20 nanosecond after the uh, ray 1 when it reaches the endpoint. So there is a time delay of 20 nanosecond between these two rays. Here the important formula is this one. The time, it is N1L by C sin phi. So it's not like you have to remember all this formula. You can easily derive it. So it's just using basic trigonometry, you can derive this formulas. Okay, so let us move to our next problem then. So it's about finding out the ray path in a square law medium. So square law, it's like parabolic index fiber. They are also known as square law medium. Okay, so it's another term that can be used for parabolic index fiber. So consider a ray launched on a square law medium at x equal to 0, making an angle theta 0 inside the square law medium with the z-axis, so that the ray path is given by this. Here you can see we have both sine and cosine. So first let us draw the schematic. So what is the general form for a parabolic index medium? General solution we have seen in 2, 3 question is x z is a sine gamma z plus b cos gamma z. Now this a and b value they depends. The gamma will remain same. That is the root over 2 delta over I think n1 root over 2 delta by a beta. So this will remain same, but only the this constant they will vary depending on the boundary condition. So here you can see we are launching a ray at x equal to x0 here. So that means at z equal to 0, we have x0 as x0. So if you put z0 here, we get b cos 0 is 1. So this is x0. That means xz is now a sine gamma z plus x0 cos gamma z. What is the other boundary condition we have now? It is the slope. So slope dx by dz at z equal to 0, it is tan theta 0. So just derivative, use the derivative of this equation. We will get a gamma cos gamma z minus x0 gamma sine gamma z at z equal to 0 is tan theta 0. So that means here, if you put z0, this is 0. So a gamma will be tan theta 0. So a will be tan theta 0 over gamma. So we find what is the value for a and what is the value for b, which is x0. Now the ray path equation will be xz is tan theta 0 over gamma sine gamma z plus x0 cos gamma z. This is what already given in the question to prove that the ray equation is like this. So next we will move to the next problem. Please go through the question once. So the question is asking about what is the maximum angle of acceptance of ray when the ray is incident at the axial point for parabolic index fiber with N1 it is given 1.75, N2 it is given 1.677 and A it is given 25 micrometer. So maximum angle of incidence means first we need to find out what is the numerical aperture, then by taking the sine inverse of this numerical aperture, we can find what is the maximum angle of incidence. And if you recall, in question number 5, we have solved the general equation for a numerical aperture. So sine I, it is less than root over of n square x minus n2 square over na. So when the ray it is incidenting on the axial point, that means nx will be n1. So there is no need to find out what is nx at different points. So that means now we have, for first part, when medium is it is 8. So that means Na is 1. So sin I max will be the numerical aperture is root over of n1 square minus n2 square. So n1 square, it is given 1.75 square minus 1.677 square. And this will come around 0.376068. So that means I max, it will be sine inverse 0.376068. And this will come around 22.1 degree. Okay. Now for the second part, the ray is incidenting on the axial point only, but the medium outside is a water. So nx will be n1, but medium in front of the fiber, it is water. So that means Na will be, Na it is 1.33. So that means I max, it is sine inverse root over of 1.75 square minus 1.677 square over 1.33. This one we know, it is already calculated here. So we'll get sine inverse it will come around 0.3760. Okay, so I think here there is a problem here. So this is not, uh, so this will come around 0.50017. So I did make a mistake here. So it is 0.500171. So the angle will be, it will come around 30 degree. Okay. Please correct that. And for here, we have 0.500171 over 1.33. This will come around 22.1 degree. Okay. So do you have any doubt till now? Otherwise, we'll solve the last problem of this live section. Okay. So please go through the question 10 once. Question 10, it's a conceptual one. So there are different refractive index profile that is given in this question. So you need to find out what should be the beta values for the guided rays, core guided rays for the following refractive index profile. So the ray should guide inside the core. Okay. So the first is says and next. So here it is N1, N2, and N3. So here the around the core layer, the cladding has two different refractive index. Okay, we used to see same refractive index inside the outside the core, but if there is a situation like this, then what is the condition for beta? Whether it lies between N1 to N2 or it lies between N1 to N3, what is it? So here you can see the highest refractive index is N1. So that means the TIR should occur at the core cladding interface here also and here also. Whatever the ray is propagating, it should get reflected. It should undergo TIR at the core cladding interface. So that means the beta tilde, the N1 should be greater than beta tilde. Now for this part, the lowest range, here you can see N2, it is greater than N3, right? So that means if beta tilde, it is greater than N2, so that means beta tilde is also greater than N3. So if beta tilde, let's say we have beta tilde greater than N2. So this means the ray is guided inside the fiber. Inside the fiber. But if you take beta tilde greater than N3, so this also means ray is guided. But if you consider this interface, so here beta tilde is not greater than N2. So that means there will be a guided mode here also. So what I mean to say, um, so there are three reasons. So if you take a value between N1 to N3, like this reason, this reason. So that means the ray will be guided inside the core and it will be reflected in the N2 interface, also in the N3 interface. But if you take a value here, that is beta is greater than N3. So if you consider a reason here, here beta is greater than N3, right? Here this is beta, it is greater than N3. But beta here it is less than N2. In this reason, beta is less than N2. And what this condition correspond to? Refracted by. Sorry. Sorry. Mm. So let me draw again. So we have um, beta tilde greater than N3. But in this situation, it is N2 greater than beta tilde, right? For this case, when beta tilde lies here. N3 and 1. Here TR will occur, but here also in this region, here you can see N2 is greater than beta tilde. So that means there is a guided ray here also in this cladding interface. So to make the ray guided inside the core, we need beta tilde should greater than N1, sorry, should less than N1, and it should be greater than N2, so that it will be get reflected both in the two cladding interface. Okay, so is this clear to you? If this is clear, then the next part will be easy for you to find out what is the beta tilde. So do you need to explain this? Okay, yes, clear. So let us see what we have for the second part. In the second part, we have uh, the refractive index profile like this. So there are three refractive index. One is N1, which is the core refractive index, and there are two cladding interface N3 and N2. So similar to the logic that we have used before, here we have to see at what optimal condition the ray will be guided. So if the ray uh, falls here, if the beta tilde falls here, so that means it is less than N1, but it is greater than N2 and as well as N3. So that means the ray will get reflection here also and reflection here also. But if you take a situation here now, if you take this is also satisfy this ray. Here the beta tilde, it is lying between N1 and N3. So it shouldn't be here, or sorry, shouldn't be here. Okay. This one is not allowed. Uh, this beta tilde is also not allowed because it's not guided. But this beta tilde, this is also not allowed because here the N2, it is 1 minute. N2 is greater than beta tilde. So that means it will not be guided inside the fiber. So we have the condition the for ray guidance is beta tilde should lie between N1 to N2 for this situation. Yes, if it is greater than N3, but it is smaller than N2, then it won't be guided. Because for that case, even though there will be guided mode, uh, which one you are talking about? Here, right? Okay. Even though inside, so this is the core reason, right? This is the core reason. So there will be guidance here, but here also we'll see a gray guidance here in the cladding reason that we don't want. So we want all the energy to propagate inside the core. So if you see the question, it is asking about which condition correspond to core guided rays. So that is why even though uh, in this problem, okay, let us say I think you are talking about this situation where beta tilde is smaller than N2. Yes, it is smaller than N2 and it is greater than N3. Here, this is the core reason. It This beta tilde satisfy lie between N1 to N, sorry, N1 to N3. So that means there is a guided ray here. There will be a guided ray here. But if you see this reason, if I take this reason, this cladding reason here, N2 is greater than beta tilde. So that means there is also a guided ray in the cladding reason. So that this we don't want because this means some part of the guided ray energy will be it will be leaked to the cladding reason. Okay. I think this is clear to you. Yeah. So you just need to identify the core reason and using that you can find out the ray condition. So now last we have this one. So here if you see the core refractive index, it is N1 and there is a N2 here, which is a depressed cladding, and there is a N3 here. So that means, let us see if the ray, if beta tilde falls here, it won't be guided because it is less than N3. So here beta tilde. So just see the condition that you are getting by taking different values of beta. In that way, you can find out what is the range. So here beta tilde is less than N3. So that means there is a guided ray in all the regions. It propagates through core, cladding, all the interface that we don't want. Okay. Next is whether it falls in this region. That is beta tilde. It is greater than N3, but it is less than N2. So if you see this ray, so this indicate that in this region there will be light guidance because N2 is less than N2 is greater than beta tilde. Okay, so this we also don't want. And so last option we have is here, that is beta tilde beta tilde, it is less than N1, but it is greater than N2. So that means we'll see light guidance in this region. So light will be guided all in this region, and it will be decayed in outside the cladding. Okay. So is this clear to you? This is all that we have for week 3. In the next tutorial, we'll try to solve the problems related to ray transit time as well as material dispersion. And if time permits, then I will see only. No, no, it's not like that. We'll cover both step index as well as the parabolic index fiber. But in this tutorial, I have basically solved parabolic because in the step index, it is a straight line. So there is no variation of ray paths. But in a parabolic index fiber, depending on the launching point, we have different ray paths, we have different numerical apertures. So that is why I have primarily focused on this. So I have discussed only the parabolic refractive index fiber. So, but as we do more tutorials, we'll see parabolic index as well as the step index, what is the material dispersion inside the medium, as well as what is the rate transient time. So we'll cover all of the situation. But in towards the end of the lecture, I think you will see why we use parabolic index fiber over step index fiber, why we use this kind of refractive index fiber profile. So we'll see the advantages of using different refractive index profile. So this is just to give you a fundamental of what can be the condition for a guidance if you have fiber like this. So in normal fiber is not like there is one core and there is one cladding. So there are different layer of cladding to make the dispersion less, to make the material dispersion less. So for that, we have different complicated fiber structure. So that is why I have solved. This last question is based on the practical fiber only. Okay. So we'll cover more. So any more question? Okay. So, okay, let us end the session. I think whatever I have covered, it is clear to you as well as the questions that I have solved. It will be helpful for you to solve the assignment problem. So we'll meet on next Monday, same time from 6 to 8. Okay. So thank you for joining the session. Have a good day. Bye.